imagine you got BCC, single crystalline material, was exposed to tensile stress, and you applied 010 load in the 010 direction. So he told you that it's tensile, so it's a uniaxial, and in a specific direction. He told you about the direction. The question, compute the resolved shear stress. That means you know that the applied tensile stress, although it's uniaxial, it will result in some shear stress according to the orientation of that plane. So he told you which plane he wants to calculate the resolved shear stress, 110. And he told you the slip direction, minus 111. And he told you how much he applied from outside. Okay? So what I need to do? Well, I need to write the equation. And the equation is saying that the resolved shear stress equals to sigma times cosine an angle, cosine an angle, right? And we said the first angle here, it doesn't matter, I mean, the first one here is related to the phi, it's phi, and this one is lambda. قلنا إنه phi, the one that's correlating the relative orientation of the angle between the normal to the plane and the applied load, lambda between the slip direction and the applied load. طيب, this is given. Sigma, he told us 52 megapascal. Now what we need to do? We need to find phi and lambda. Okay. How to find it? Now you have an angle between two vectors. We will be using this equation to calculate to find the angle between the two vectors. What are those vectors? Well, let me draw it here. This is the whatever you are applying, and this is the parallel to the surface, and this is the normal to the surface, and this one is lambda, and this one is phi, right? Phi. The slip direction, he told you it is minus 1, 1 slip direction. So let me erase this. Let me have the same. Let me go to here. Okay. So the slip direction is minus 1, 1, 1. But what is the normal direction? What is this vector? Because it's perpendicular to this plane, it will have the same indices as the plane. So what is the plane? The plane is 110. So this the direction of the normal to the plane will be 110 in cube, in cubic system. In a cubic system, you can apply this rule. طيب, بالتالي 110. So what is the direction of the slip direction? Okay, he told us, right? He said it is minus 1, 1, 1. Good. Now I know this is minus 1, 1, 1. What else I know? Well, I know the direction of the load is 0, 1, 0. Right? طيب. Now what I will do, I want to calculate the angle lambda, for example. In order to calculate lambda, what I'm going to do, I'm going to say minus 1 times 0, minus 1 times 0. So this times this, and then 1 minus 1 times 1. So 1 times 1, and then 1 times 0, 1 times 0. I'm going to do the same thing here, and by doing so, I will be able to calculate the angle lambda. I will do the same thing between these two vectors in order to calculate the phi. Okay, so let's go to the next page. So if you go to the next page, this is phi. You plug the numbers, you got 45 degree. For the lambda, you got 44 degree. And then you're gonna plug these two numbers in the resolved shear stress. That would allow you to calculate the resolved shear stress, 21.3. So the 52 megapascal, the applied tensile stress, will result in some shear stress, right, equals to 21.3. But that shear stress is not enough to let the dislocation move or slip, right? So the second part of the question, يقول لك, if slip occurs, إذا كان الديسلوكيشن حيمشي على نفس البلين ونفس الدايركشن, وقال لك الكريتيكال resolved shear stress is 30 megapascal, calculate the magnitude of the applied stress necessary to initiate the yielding. Remember, we were able to correlate between sigma y with critical resolved shear stress, right? So I plug the critical resolved shear stress. I have the same angle between the planes, right? Then between the plane and the axis, or these angles that will describe the orientation of the plane, that will allow you to calculate sigma y. Now, the sigma y turned out to be 73.4 megapascal. This is the needed stress in order to initiate the plastic deformation. If you want to get more details, okay, this is the needed stress in order to result in the critical resolved shear stress of certain plane. That plane will be activated, and if it's activated, the dislocation will slip on that plane, and that slipping of dislocation will result in plastic deformation. Okay, good. What about if you have polycrystalline material? So in polycrystalline material, we are dealing with grains. We are dealing with grains, right? Let me delete this. We are dealing with different grains, right? We're dealing with different grains. Now, those some of, maybe the applied stress from outside will result in the critical resolved shear stress in this plane, right? The critical resolved shear stress of a certain plane in this grain, right? But that value still is low enough, it does not activate any plane here. So then what's going to happen? This will be activated, this location will start to move, but you notice the result of slipping of this location of a polycrystalline material will be not only as the result of a single grain, it's the result of all the grains. And now, maybe the applied stress activated some planes in this grain, but not in this grain. Or maybe the activate one in will be in different direction than the one that you have it here. What I want to say, the resistance to plastic deformation in polycrystalline material is higher than single crystalline material, because there are some constraints on the grain boundaries. So those grain boundaries are rigid, cannot be broken, okay? And whatever respond of a grain boundary will not determine, or a grain, or whatever respond of a grain will not determine the behavior of the material, because at the end you have to look at the average performance of, or average behavior, or what happened to all the grains in the polycrystalline material. Now you see, for example, sometimes the applied stress might result in activating more than one slip system. Do you see parallel line here? Parallel line, and then you see some intersecting lines. right? That mean more than slip system was activated in a single brain. Okay, so this is what I wanted to say for today, and I will stop here and we'll continue the discussion in next lecture, inshallah. So let's see if you have any